Okay, how we doing there, guys? Commenter come, not commenter come? How the 2011 looking? Alright, so let's check that one on the board. Oops. Alright, so this is the 2011 trig proof. It's 2011. Alright, so this is question 4, part C. Again, you're writing looking like a shivering right through, boy. Question 4, part C. Alright, cool. So we are required to prove the following. So tan theta minus 1 over cos theta all squared is identical to minus sin theta over 1, sin theta minus 1, sorry, over sin theta plus 1. Alright, so did you guys get that one out? The balance back? No? Alright. Okay, so which side seems to be the logical side to start with? Left side or right side? Left side? Alright. Yeah, I think so too. So, here's my question. Did you all expand first, or did you all try to simplify inside the bracket first? Remember, we saw that we could do that last week, right? Simplified? Okay, let's try that. So, taking the left-hand side, left-hand side, sorry, so tan can be written as sin theta over cos theta minus 1 over cos theta all squared, right? So of course we have a fraction, right? So we could use a common denominator because we are subtracting, and fortunately for us they have the same denominator, which is cos theta. So we're going to get sin theta minus 1 in that numerator, which we then have to square. Sorry. So we apply, when you square something, you multiply by itself. So essentially what's going to happen is you're going to end up with the square of the numerator over the square of the denominator. Now check this. Before you apply distributive law and expand the numerator, notice where we have to go. Sin theta minus 1, right? So do we have a sin theta minus 1 in the numerator already? So let's see if we can maintain that for now. So before you start to expand, what you could do if you want is you could express it as such. So sin theta minus 1. Remember, when you square something, you multiply by itself, right? Sin theta minus 1. Now, when you square cos theta, you're just going to get cos squared theta, right? So instead of having to write all that over, cos squared theta. Now, in the final result, is there any ratio, any trig function besides sine? So there's no cos, no tan, right? There's only sine. So can we convert cos squared to sine squared by somehow? How do we do that? 1 minus sine squared, right? Alright, so 1 minus sine squared theta. And we know 1 minus sine squared theta is the difference of 2 squares, not so? Okay, so let's put back that sine theta minus 1 by sine theta minus 1. And we could have in our denominator 1 minus sine theta and 1 plus sine theta. Now, if we look once again at our answer, we just have sine theta plus 1 in the denominator, which means we have that already there. And we have a sine theta minus 1 in the numerator, which we already have as well, don't we? We have it here. But the problem is we have in both the numerator and the denominator something to the front attached to it. But the thing is, they aren't the same, so we can't exactly cancel them out. And that's where this minus sign comes in very handy. Right? So we know, or if you don't know, you're going to see now, right? That factorizing with minus 1 is a very useful tool to help get us out of little jams like this. Right? Let me show you. So let's just put back that numerator very quickly. So sine theta minus 1 by itself, sine theta, oops, sine theta minus, I'm grateful that the scratch erase is working. Now, if you factorize with minus 1, this item here minus 1, what's going to happen? Let's just take a look below. So if we pull out minus 1 as a common factor, what do we do to get the inside of the bracket? We divide each item by the common factor. 1 divided by minus 1 will give us minus 1. Minus sine theta divided by minus 1 will give us plus sine theta. And we could rearrange minus 1 plus sine theta to get what? Sine theta minus 1. And we could rearrange 1 plus sine theta to get sine theta plus 1. And guess what happens? This cancels with that, not so? And then that minus sign could simply come to the front, and we have sine theta minus 1 in the numerator and sine theta plus 1 in the denominator. So yeah, so this one was a little tricky with that little trick. Yes, question? Oh, okay. Yes, so it was a little tricky, and you had to know about this particular factorization. Now, there could very well be other ways to go about solving this. This is just the way we did it today, right? And I'm sure when I was working for the first time, I probably expanded this bracket here, right, without without simplifying it first. And that gives you a bit more working to do, right? It is valid. I'm not going to say it's not valid, right? So if anybody did it, right, don't be ashamed or anything, right? Of course, the more steps you have in your working is the more chance there is, or the greater the risk that you're going to make an error somewhere. Every step is a possibility of a risk of an error. All right, but don't be afraid, right? And it will teach you to pay attention to what you're doing. Okay. Okay. So 2012, right? Paper 2, question 4, part C. We have to prove the identity 1 over sec theta plus tan theta is identical to 1 minus sine theta all over cos theta. All right, so which side you'll feel like taking here? Left side, right side? Left side? Okay, let's go. Taking the left hand side. All right, so let's convert one time. So 1 over sec. So sec theta, we know is 1 over cos, right? And tan theta, we know is sine theta over cos theta, right? So doesn't this resemble something we just did? When I say if you ignore the 1 over, right? The first question had something similar on that side, right? Now, what we could see here is because we have a common denominator in the denominator, we could simply combine these fractions as 1 plus sine theta all over cos theta. And of course, we know if we have 1 over that, 1 over a fraction will cause us to invert the fraction. So this will, if you want to see it in detail, you can take the numerator, and the understood operation between numerator and denominator is division, right? So we're dividing by 1 plus sine theta all over cos theta. And of course, when you're dividing with fractions, what's the protocol? You change divisor, multiply, and what do we do to the divisor? We invert it. Okay, so now we have just come to a point where we have cos theta over 1 plus sine theta, and it looks basically like the inverse of what we have to get, with the major exception that instead of 1 plus sine theta, we need to get 1 minus sine theta. And that in itself is a hint, right? So we want to kind of get the 1 minus sine theta on top and the cos below. So this is where our, well, quote unquote, rationalization of the denominator using difference of two squares comes in. So we have to multiply by 1 minus sine theta over itself. Alright? So what would happen is that in your numerator now, you're going to get cos by 1 minus sine theta. Sorry. Your denominator, now 1 plus sine theta by 1 minus sine theta, that's perfect setup for what? Difference of two squares. So that's simply going to give us 1 minus sine squared theta, which we know is what? What's 1 minus sine squared? Cos squared, right? Okay. So we have cos squared in our denominator. And look at that, we could cancel the numerator, the cos in the numerator can cancel with the cos squared in the denominator, leaving us with 1 minus sine, 1 minus given theta, sine theta all over cos theta. Okay, so we have here the 2014 paper 2 question 4 part C. We are required to prove that tan theta by sine theta over 1 minus cos theta is identical to 1 plus 1 over cos theta. All right, so yeah, so this one was a little bit of a tricky one because of that denominator and the fact that it was a fraction. So what I'm going to show you guys now is a slightly different way to work it based relative to the ways I worked it before. Okay, so the first thing that you can do when you encounter fractions like these, especially when you have a 1 minus cos in the denominator, is you could actually simply do this, right? So let's just say taking left-hand side, right? So taking left-hand side as per usual, right? So we could simply separate this into the items in the numerator over 1 multiplied by 1 over 1 minus cos theta. What this allows is it allows us to kind of work with the numerator freely and unencumbered by the denominator, and sometimes in certain instances less confused, right? Now, the only thing we could really manipulate here, okay, well, let me not say that. The thing we should probably manipulate first is tan theta, right? How else can we express tan theta? Sine theta over cos theta, right? So you're going to have sine, sorry, the second e, right? So sine theta over cos theta multiplied by sine theta, right? Over 1, as all over 1. And this item on the right-hand side here is just unbothered by what's going on that side. So here now, when you're multiplying fractions, you multiply numerators by numerators and denominator by denominator. So what's sine theta by sine theta? Sine squared theta. And you're going to get that over cos theta. Now that is over 1, and we're multiplying by 1 over 1 minus cos theta. Now we can simplify this item by simply dropping the over 1, right? Imagine this was just x. Isn't x over 1 equivalent to x? Right? So what we could do is simply express it as sine squared theta over cos theta multiplied by 1 over 1 minus cos theta. We could bring together these things here as they are. Right? So that's one thing we could do, but I'm going to take a different route today, just because it is today. Sine squared. Now, if we notice in the final result, what's the only trig function or trig ratio we have there? Cosine, right? Currently in our working, we have a sine squared. Can we convert sine squared somehow to cos squared or something? Yes. What would it be? 1 minus cos squared, right? So we'll do 1 minus cos squared theta all over cos theta multiplied by 1 over 1 minus cos theta. We know that 1 minus cos squared is the difference of 2 squares. So we could express that as 1 plus cos theta, by 1 minus cos theta all over cos theta multiplied by 1 over 1 minus cos theta. Sorry, that didn't come out too right. Okay, and guess what's going to happen here now? This will cancel with that, leaving us with what? 1 plus cos theta over cos theta. And now this is where what actually was thinking about doing could come into play, the decomposition of the fraction, splitting it apart, right? So we could pull the 1 over cos theta by itself and then have cos theta over cos theta by itself. And guess what that will cancel down to? Cos theta over cos theta is 1. And we have gotten the solution, right? 1 plus 1 over cos theta is, what is going on? Right? Is the same as 1 plus cos theta, 1 over cos theta plus 1. All right, so once again, just to recap the process there, right? Let me just, right, so the first thing I did was I separated the left-hand side into the numerator multiplied by 1 over the denominator, right? Sometimes that helps people to see things and to be able to work with things separately. Sometimes when it's all jumbled as a single fraction, it tends to get cluttered, and when things are cluttered, we tend to get confused, right? So if you could pull it apart and just keep it separate for now, you could recombine it at any point in time, right? But it's just a strategy to try to minimize the clutter and confusion. So now we could work with that numerator by itself, right? So tan theta was sine theta over cos theta, and that was multiplied by the sine theta, which was this item here, right? Sine theta by sine theta gave us sine squared theta, and that's all over cos theta. And yes, that was over 1. So this itself was a numerator. Now, when we simplified that, we got down to sine squared theta over cos theta multiplied by the same item from early on in the question. From there now, we said, okay, look, we considered the final result. The only trig function there was cos theta. So we said, okay, look, what we have? Well, we have a sine squared. How do we get rid of that sine squared? Well, especially and in the context of getting it to a cos. And we said, okay, sine squared is 1 minus cos squared. So we did that. So I don't know why it keeps doing that menu thing. Right. Stop it. Stop it. Behave. Just behave. Right. So, like I was saying, sine squared could convert to 1 minus cos squared. And that there is the difference of two squares. So we could separate that, or factorize it rather, as 1 plus cos theta by 1 minus cos theta. And then in so doing, what would happen is that 1 minus cos theta in the numerator would cancel with the 1 minus cos theta in the denominator to which it was attached initially. Whoops, sorry. All right, and then when that happens now, we're just left with this piece here, 1 plus cos theta over cos theta. And then we can simply decompose the fraction. Whoops, doesn't want to erase. Behave yourself, man. All right, fine. Right, so you get 1 plus cos theta, 1 over cos theta, sorry, plus cos theta over itself. And then cos theta over cos itself will just cancel to 1. And we have our result. Okay, so this is the 2015 paper 2, question 4, part C. We are required to prove that sine theta plus sine 2 theta over 1 plus cos theta plus cos 2 theta is exactly identical to tan theta. So that's a lot of stuff on the left-hand side to just kind of boil down to the stuff on the right-hand side. So I think, the right-hand side doesn't give us much scope to work with, right? So the left-hand side is probably what we're going to start with, right? So let's go. So taking left-hand side. Okay, so in the numerator, we should probably expand sine 2 theta. Anybody remember the expansion? That'll give us 2 sine theta by cos theta. The denominator, we have 1 plus cos theta. Now cos 2 theta could expand if you want to start with just cos squared theta minus sine squared theta, might give us some scope to work with, right? Now, once again, be mindful of where you're going. To tan theta. Tan theta is simply sine over cos. So we might want to try to lean towards having only cos in the denominator, but we could take a look and see what happens, right? Yeah, in your numerator, what I'm seeing here is the possibility to factorize with sine theta as 1 plus 2 cos theta all over now. So let's see, what could we do with that denominator? Well, if we, once again, like I said, let's see if we could just carry that to the cos squared version, which would be plus 2 cos squared theta minus 1. Now if we do that, the 1 minus 1 will cancel out, leaving us with 2 cos squared theta plus cos theta. So that numerator kind of still stays as it is. Right, so we have 2 cos squared theta plus cos theta. And just like we factorized in the numerator with sine, we can factorize in the denominator with cosine, because that seems to be the common factor there. So let's pull out cos theta. Sorry, right, cos theta. That'll give us 2 cos theta plus 1, which is the same as 1 plus 2 cos theta. So it looks like this will simply cancel with that, leaving us with sine theta over cos theta, which will give us tan theta. Right, so yeah, once again, you had to know your double angle expansions to facilitate. Everything okay?
Yeah. It's a very
long route to get there. Yeah. Once again, as I said, I always try to keep it in context of where we're going. right? So if you remember, tan theta really only is sine theta over cos theta. I mean, yeah, you could have 1 over cot and that kind of stuff too, but that 1 over cot is still sine theta over cos theta, right? So all I did was, once again, expand the sine 2 theta in the numerator, expand cos 2 theta in the denominator, right? And as a matter of fact, you could have gone actually straight to that expansion if you wanted, with just the cos squared, right? I chose to go here just to kind of illustrate, you know, we could start there and then progress to other things. Now when you expanded the sine 2 theta in the numerator, we found that we had scope to factorize, because you had sine theta plus 2 sine theta cos theta. Taking out sine theta from there will leave us with sine theta by 1 plus 2 cos theta, right? Meanwhile, in the denominator, when I expanded cos 2 theta, I got cos squared minus sine squared, which I turned to 2 cos squared minus 1. Now why I did that, like I said, it was just a hunch I had because we had to go to tan theta, so I was trying to aim to go to sine theta over cos theta. So the numerator already had sine theta, but it was attached to something, so chances were that this would end up having to cancel off with something in the denominator, right? And like I said, I wanted to go to cos theta only in the denominator, so that's what I aimed to do. So I converted this to that, and then the 1 minus 1 will cancel the 0, leaving us with cos theta plus 2 cos squared, right? You didn't have to rearrange it. As a matter of fact, if we didn't rearrange it, it would have actually looked exactly like how it was supposed to look. But because of commutative law, we know that 2 cos theta plus 1 is the same as 1 plus 2 cos theta. So in any case, like I said, we were left with the 2 cos squared plus cos. We factorized with cosine, giving us the 2 cos theta plus 1 in the bracket, which would then cancel with the 1 plus 2 cos theta in the numerator, leaving us with sine theta, or as I have here, gin theta, I don't know. Could you just run S? Right, okay, thank you. And that, as they say, was that. Alright, so we want to take a look at the 2016 paper 2 question 4 proof. Alright, so it says required to prove that sine of theta plus alpha over cos theta cos alpha is identical to tan theta plus tan alpha. So remember, like I said, always think about where you're going, right? Tan theta, tan alpha. What's tan theta? How else can we express tan theta? Sine theta over cos theta, right? What about tan alpha? Sine alpha over cos alpha, right? Okay, so bear that in mind, because here, don't we see a cos theta and a cos alpha there? Alright, now the numerator, we could use the sine of a plus b to expand that. What's the expansion when you expand that? You're going to get sine of theta by cos of alpha, good, plus cos of theta by sine of alpha. And that's all over cos theta by cos alpha. And what we could do here, like I was saying, is we decompose the fraction. We kind of cut it in half. We put each aspect of the numerator over the common denominator. So we'll end up with sine theta cos alpha over cos theta cos alpha plus cos theta sine alpha over cos theta cos alpha. And guess what happens there? Cos alpha cancels with cos alpha, cos theta with cos theta. So we end up with what? Sine theta over cos theta plus sine alpha over cos alpha. And that simply gives us tan theta plus tan alpha. Right? So remember that trick about decomposing the fractions, splitting them apart. Right? It works usually when you don't have a sum or a difference in your denominator. When it's a single term or a product, right? You can do that. You can, and especially if your numerator has a sum or a difference, you can split that into each part over the common denominator, right? For example, let's say I had x plus y plus 2 all over 3. This could simply become x over 3 plus y over 3 plus 2 over 3. Right? So decomposing a fraction could help you to simplify things or to get the answer. Okay, so 2017's proof was 1 minus cos squared over 1 plus sine theta. All right, and that's identical to sine theta. So you might look at it and think, well, how does that boil down to sine theta? Right, now my first instinct here was to go after the denominators, simplifying the fractions. But then I looked at that cos squared again and I said, look, hold on. Where am I going to? I'm going to something with only a sine theta. Can I get rid, or can I convert any other non-sine theta things to sine theta? And the answer is yes. So what about instead of simplifying the fractions, I converted cos squared theta into 1 minus sine squared over 1 plus sine theta. And then I remember that 1 minus sine squared is equivalent to a difference of 2 squares. Right? So what I could do there is do a factorization of 1 minus sine squared as said difference of 2 squares. Oops, why is my pen not writing? Oh, there you go. Back on. Cool. Which would then facilitate the cancellation of the 1 plus sine theta between the numerator and denominator, leaving us with 1 minus sine theta. And when we drop that bracket, guess what happens? You get 1 minus 1 plus sine theta. And what's 1 minus 1? 0. And 0 plus sine theta leaves us with sine theta. Right? So once again, a lot of times our initial instinct is to simplify the fractions, which I know I probably did the first time I did this, most likely, right? But after working these questions a couple of times, you realize, wait now, or even the questions from last week from exercise 7.4, you realize, look, cos squared, 1 minus sine squared, 1 minus sine squared, difference of 2 squares, 1 plus sine, 1 minus sine. You could cancel the 1 plus sine between numerator and denominator, leaving us with this, and then that, right? So sometimes you have to consider all the options, but other times if you try to consider all at the start, you wouldn't start at all. So yeah, best to just dive in, right? Sometimes, like I said, at least you're hitting the roadblocks now, so when the exam comes, you see all the tricks, so you know what to try, right? So don't worry about it too much. All right, so the 2018 identity. All right, so we have the difference of two fractions here, right? We have 1 minus sine x, 1 over 1 minus sine x minus 1 over 1 plus sine x. So the thing is, we know that the only real option here, unless you're trying to go real technical, is we have to simplify the fractions, which will require a common denominator. And in this particular case, it'll just be the product of the two denominators, the LCM, right? So we'll get 1 minus sine x, good writing, 1 plus sine x. So of course, when you divide into that, right, you end up multiplying, would this erase please? Right, you end up multiplying that numerator by the 1 plus sine x, yes? Okay, so we get 1 plus, come on man, it's the last question, leave yourself. Right, 1 plus sine x, minus now. So when you go this into that, you end up multiplying this numerator by 1 minus sine x, yes? Right, so you have minus, in brackets, 1 minus sine x. Now what happens to 1 minus sine x when you drop the bracket? You get minus 1, but you get plus sine x. And 1 minus sine x by 1 plus sine x will give us what? 1 minus sine squared x. Now in the numerator, 1 minus 1 will cancel to 0, and sine x plus sine x will give us 2 sine x. And of course, 1 minus sine squared in the denominator will give us cos squared x. Now look at where we're going. We want 2 tan x over cos. And we know that tan is sine over cos. So we have 2 by sine over cos all over cos again. Now how does that help us? So once again, we kind of have to decompose this fraction, but it's not in the sense of splitting apart the numerator. We're simply going to split apart the numerator and denominator into components like this. See that? And then further, we could split apart that denominator again. Because how do we get cos squared? We multiply cos by itself, right? And we could combine these two to get what? 2 sine x over cos x, which will give us what? 2 tan x, right? And then finally, when you fully get to the last part here, 2 tan x over cos x. right? So, once again, the first step that seemed very logical to me and natural was to simplify the fraction using the LCMs and of course modifying the numerators appropriately. After that then, when you drop the brackets, we were able to cancel down things to 2 sine x in numerator. The denominator was the difference of 2 squares, which gave us cos squared x, and then we split apart that fraction into its components and then regroup things and then recombine them in order to facilitate getting to the final answer.